We're going to be talking about solubility reactions, and solubility reactions are really what are called double replacement reactions. The general formula for a double replacement reaction is AB plus CD produces AD plus CB. And I'll explain what this means with a reaction in just a minute. So whenever you have a double replacement reaction, one of the products that forms is a precipitate, and another one of the products is going to be aqueous. So you have two aqueous solutions coming together, and you produce a precipitate and an aqueous solution. If a solid is produced, then the reaction produces an insoluble precipitate. If the reaction proceeds and two aqueous solutions are produced, then the reaction is considered soluble. Let me show you what that looks like. So in a double replacement reaction, you have two ionically bonded aqueous solutions coming together. An example of that would be aqueous sodium sulfate added to magnesium carbonate, which is also aqueous, to produce sodium carbonate and magnesium sulfate. All right. So in this example, you have A, B plus C, D produces A, D plus C, B. And in this situation, sulfate gets a letter, carbonate gets its own letter because they're polyatomic ions. And so they're basically partner switching. So sodium was with sulfate, but it reconnects and combines with carbonate, and then magnesium was with carbonate in the reactant side, but it reconnects with sulfate on the product side. In order to determine the states of matter and determine if this is a solubility reaction or if an insoluble precipitate forms, we have to look at the solubility chart. So when you look at the solubility chart, you're looking for both of the products to determine if they're soluble or insoluble. So let's start with sodium carbonate. Over here on this column, you look for your negative ion, which would be carbonate, that's your anion, and down here, here's carbonate. So carbonate plus any alkali ion or ammonium is going to be soluble. Well, sodium is a group 1 alkali metal. Therefore, carbonate plus an alkali ion, meaning sodium, is going to be soluble. Therefore, this compound, sodium carbonate, is going to be aqueous. The second compound is magnesium sulfate. So we look for sulfates and find it right here. Sulfate plus any of these ions is going to be insoluble. Sulfate plus anything else is going to be soluble. Well, because magnesium is not on this list, it has to be any other positive ion, therefore it is also soluble. So this reaction is a solubility double replacement reaction because there is no precipitate formed. They're all aqueous. Another example of that reaction where a precipitate does form, copper sulfate, which is aqueous, combining together with sodium phosphate. In this situation, copper is A, sulfate is B, added to sodium, which is C, phosphate, which is D. They're going to recombine. So I know that this is copper plus 2 because sulfur has a -2 charge. So when copper recombines with phosphate, it would be Cu plus 2 plus PO4 minus 3, and so it would produce Cu3 PO4 2, and so that would be my compound that goes here. And then sodium, so copper is A, phosphate is D. And then I know that C and B are going to combine. And so C is sodium, and B is sulfate. So I'm going to end up with sodium sulfate. So my second compound will be sodium sulfate, which is C and B. All right, so then let's look at our solubility chart. And we're going to be looking for copper phosphate and sodium sulfate. So let's do sodium sulfate first because I found sulfate. So sulfate plus any of these is insoluble. Sodium is not on this list, therefore it is going to be soluble, which means that it's aqueous solution. And then copper 2 phosphate. I look for phosphate, I found it right here, plus any alkali ion or ammonium is going to be soluble. Well, copper is not either of those, which means that it is any other positive ion, which means it's going to be insoluble. Therefore, this forms a precipitate, so it would get a solid right there. So that's a precipitate formed. All right, so then let's back this up really quick. These equations, particularly the second equation, is not complete. I'm going to rewrite it. This is a double replacement reaction that produces an insoluble precipitate. So I have to make sure that it abides by the law of conservation of matter. So one of the things that we need to do is balance the equation. And so what I'm going to do is I'm going to put lines in front of each of the compounds. And then I'm just going to go through and I'm going to count them. Make sure that the elements are in equal quantities on each side of the reaction. So in my reactants, I have 1 copper. In my product, I have 3 coppers. So what I'm going to do is I'm going to put the number 3 there in front of copper sulfate, and this 3 is going to distribute to the copper. So now I have 3 coppers here and 3 coppers here. The next thing I need to do is to look at the sulfate. Whenever you have a polyatomic ion, it's best to look at it as a whole versus individual elements. So to me, this says that I have 3 coppers and I also have 3 sulfates. Over here, I have 1 sulfate. So what I'm going to do is I'm going to put the number 3 in front of this compound. I already had 2 sodiums, and now I have 6 sodiums, and I also have 3 sulfates. Okay, so my sulfates are now even, my copper is now even. Coming back over here, because I had to put a 3 here, I now have 6 sodiums. I would need to put a 2 here because these multiply. 2 times 3 is 6 sodiums, so now those are even. And this 2 distributes also to the phosphate. So I have 1 phosphate right here. Well, I now have 2 of them because the 2 distributes to the entire phosphate. Well, if you look over here, I already took care of my coppers. I have 3 coppers here. And look, I have 2 phosphates. So step 1, write out the reaction. Step 2, balance the equation. Step 3, find the states of matter, which is either going to be aqueous or solid if a precipitate forms.